to find the conjugate complex of the complex number 1 by 1 plus I. Now in order to find the conjugate complex, first we have to convert this into A plus IB form. In order to convert this into A plus IB form, we have to rationalize. So we'll rationalize the denominator. Its rationalizing factor is 1 minus I. So we'll multiply and divide the given complex number by 1 minus I. So 1 into 1 minus I is 1 minus I by 1 plus. We know that I square is minus 1. So this will become plus 1. So the given complex number is nothing but 1 by 2 times of 1 minus I. Now, the conjugate complex of this number is nothing but 1 by 2 times of 1 plus I, which can be written as 1 by 2 times of 1 plus I. Again, if I further rationalize this by 1 minus I into 1 minus I, then this will be half of 1 plus 1 by 1 minus I, which can be written as half into 2 by 1 minus I. So the required answer is 1 by 1 minus I, which is nothing but option A.
Below given circuit, find the effective resistance between the terminals A and B. So V is equals to, that is VAB is equals to I by 3 R plus I by 6 into R, I by 3 into R. So 2I by 3 I by 6 into R, which is 6 4I and I into R. So VAB by I is nothing but RAB, which is equals to 5 by 6 R. That is option B is correct. In a biased JFET, the shape of the channel is as shown in the given figure. Why it is? Because see, we have to tell the reason why the channel shape is like that. So this channel shape is nothing but a wedge shaped. It is because here, if we take any JFET, this is drain, this is source. So suppose if we assume this is an n-channel JFET, here this is VDS, this is VGS. Now here this n-channel substrate acts as a resistor. So as you move towards the drain end, the voltage drop across the channel is going to increase, which will cause the more reverse bias towards the drain end compared to the source end. So that's the reason why the depletion region is penetrated more here, because this is P, this is also P. Those two gates are shorted together. Now hence the depletion region is more penetrated into the channel towards the drain end compared to the source end. That's why option B is correct. That is, drain end is more reverse biased than the source end. Option B is correct. An n-channel enhancement type MOSFET, if source is connected at a higher potential than that of bulk, then the threshold voltage of the MOSFET will be. Here we know Vt is equals to Vt naught if VSB is equals to 0. That means the source potential is equals to the body potential or substrate potential. In that case, Vt is equals to Vt naught. So if VSB is greater than 0, that means here body effect is going to play a significant role in deciding a threshold voltage. That is Vt naught plus a body effect parameter under root surface potential 2 pi f and VSB minus 2 pi f. So in that case, if VSB increases, threshold voltage increases. That is, option A is correct. It has the following specifications. That is VIH min, VIL max, VOH min and VOL max as given in the question itself. We have to find out the respective noise margins of the logic family for the logic high as well as the logic 0. See, we know the logic levels can be represented in the block diagram as in the boxes. This is VOL max. This is VOH min. This is VIL max. This is VIH min. That is, here this one and this one. These differences are noise margins. This is nothing but noise margin in the logic high level. That is, VOH min is 4.8 volts minus VIH min is 3.9 volts. That is 0.9 volts. This is noise margin in case of low level, that is VIL max minus VOL max. That is 0.8 minus 0.2, that is 0.6 ohms. That is, option A is correct. An N-channel JFET has IDSS equals to 10 milliamps and VP equals to minus 4 volts. Determine the minimum value of VDS for which the pinch-off region, VGS equals to minus 2 volts. That is, VDS min is. Here VDS for the pinch-off region should be VGS minus VP. So VDS min is equals to VGS minus 2 plus 4, which is equals to 2 volts. That is, option A is correct. Open circuit works as. Here, if we apply a KCL at node A, I1 plus IF equals to 0. Here V0 is nothing but IF minus IF into RF. So here IF is equals to minus I1, that is I1 into RF. So I1 is decided by IS. Hence, input parameter is current and output parameter is voltage. Hence, it is nothing but current to voltage converter. That is, option B is correct. Resistance of a non-inverting op amp is. Here, Rin is nothing but this. So, Rin is equals to V1 by I1. Here, this node potential is V1, so this. So, if we apply a KCL here, that is I1 is equals to V1 minus V0 by R. This is equation 1. Similarly, if we apply at this node potential V1 by R1 plus V1 minus V0 by RF. So here we have to eliminate the V0 variable in the equation 1 in order to get an equation only in terms of V1 and I1. So V1 R1 RF divided by R1 plus RF, this is RF, equals to V0. So V0 is equals to V1 R1 plus RF by R1. I1 is equals to, we have to substitute this into equation 1. So V1 by R minus 1 by R. V0 is, this is V1 R1 plus RF by R1. So I1 by V1 1 by R minus 1 by R 1 plus RF by R1, that is RF by R1 into R. So R input resistance is V1 by I1, so R1R divided by RF. So option B is correct.